All right, hey everybody, welcome back. So what I wanted to do for today's class, I wanted to start out with a bit of a review session. So what I was thinking I would do, because I've been getting a bunch of questions, especially about linear algebra and vector spaces, what I was going to do is go back through go briefly through all of the recent lecture notes on linear algebra. And then what I was thinking I could do is that I could solve example problems on any topics that students have questions about. So while I'm going through these lecture notes, if people could think of example topics that they'd like to have examples about, I can then try and make an example problem on the fly and show you how to solve it in any of these topics. So this can be about preferably the topic that I'm going over at any given time, but please feel free to send these questions to the TAs on any topic, and especially if you feel like you don't have enough understanding of a topic to propose a concrete question, feel free to ask a vague question as well, and I'll do my best to just do examples that will hopefully help people understand what all of these topics are about. So let's get started. We'll go to the slides. So the first concept for linear algebra is a vector space. So we had notes on vector spaces. You guys have hopefully all seen Rn as a vector space. Okay, so I'm starting to get the first questions already. People would like to start with questions about the exercise that's due tonight. That makes sense. All right, let's start with questions about that exercise. So I happen to have that assignment up here. So the key question that people seem to be asking is what are the centers and the dot products? Okay, so let's get a whiteboard here. So we have a vector space that we're looking at here, which is we're calling it V. I don't know why my pen isn't working right now, but let's hope that we can get it to work. There we go. All right, so we have a vector space V, and that's equal to the span of a whole bunch of functions, right? And so those functions are of the form qx, right? So the function qx takes an argument y, and it maps it to x of minus 1/2 x minus y squared, right? So that looks like this, right? And the center here, this would be x, right? And then the argument of the function is the horizontal function. So this is qx of y. This here is x, and then the horizontal axis here is y, and the vertical axis is qx of y, right? And so x here says where the function is centered, meaning what is the highest part of the function. And so we're calling the x's the centers, right? And we gave a list in the assignment here, right? So down here we have this set of centers here, right? And so V is the span of the set Q1, Q3, Q5, and so forth, right up through Q48, Q49, Q50, right? So these 35 different functions, each of which is a q sub x with its center at one of the points in that list, right? And so what do functions in this vector space V look like? They look like linear combinations of these basis functions. So for example, if I have, here's another set of axes, right? So Q1 is centered here at 1, and it falls off like that. Q3 is centered here at 3, and it falls off like that, right? And a linear combination of those two functions would look something like, let's say it has a positive coefficient on the first one and a negative coefficient on the second one, right? And it would look something like that. So this would be something like Q1 minus a half of Q3, right? So that's the vector space of functions we're working with. Then the other question people had is, so that should answer what is the question of what are the centers. The other question people asked were what are the dot products, right? So let's go to a new page here, right? So we gave in order to figure out how to represent the function f in our basis, meaning in the span of these q sub x where x is a center, we need the dot product of our function f with each one of our basis elements, right? So we have a dot product between, let's say, f and let's say q sub 5, right? And so we have a list here of these dot products. These are the dot products in the same order as the center. The dot product between f and q1, between f and q3, between f and q5. And so in particular, that is 9.939, right? So those are the quantities that, that you should need in order to be able to express this function f in the given basis. And that's what we're asking you to do for the exercise, is to discover what is that function f. In particular, what are the coefficients, right? So we want to write f is equal to some number times b1 plus some number times b3 plus some number times b5 and so forth, up to the end where it's some number times b50. Let me write this. Sorry, the basis functions are each one of the q's, so I should write this as q1, q3, q5, all the way up to some number times q50. Right? And so the 1, 3, 5, these are the numbers in the centers, and these coefficients here, we were calling them up here in this right up here, right? We were calling these x tilde sub I. So this is x tilde sub 1 corresponding to b1, where b1 is equal to q1, plus x tilde sub 2 times b2, where the second basis function is equal to q3, plus x tilde sub 3 times b3, and the third basis function is q5, right, and so forth. So hopefully that clarifies what the given problem data is. If not, please feel free to ask more questions, and I'll try to answer them. For now, let's go back to these notes, and feel free also to ask questions about the notes. So vector spaces. Everybody should be familiar with Rn, right? That's the set of length n, n element vectors of real numbers. And Rn is a vector space. It's not the only vector space, but it is a vector space. And what makes it a vector space is that you can do things like add together two vectors or multiply a vector by a scalar. And these properties, these operations, they satisfy the laws that you expect them to for Rn, which is to say, for example, that addition is commutative, that addition is associative, that scalar multiplication distributes over addition, and that there's a zero vector, which is the vector that when you add it to any other vector, it stays the same. So that's what makes it a vector space. And there are tons of other vector spaces out there in the world. Let's see. I'm getting a question. Oh, back to the problem. The question is whether does BI equal QI? The answer is no. Right? BI is not equal to QI. So we have the set B1, B2, right, up to B35, right? So these are numbered in order, the 35 different basis vectors. That is equal to the set Q1, Q3, Q5, right, all the way up to Q50, right? And so the basis vectors, right, these are, if we look down, if we look down here, right, so the this is the first one, this is the second one, the third one, the fourth one, right? So we can index it into them either by their position in the list, that's what BI is doing, or we can say what is the actual number at that position, right? So 13 is one of these numbers, and Q13 will be part of our basis, and it will be the 1, 2, 3, 4, 5, 6, 7th element of our basis. So B7 is equal to Q13. And the subscript of Q doesn't have to be an integer. It happens to be in this case, right? But the subscript of Q is any real number, because if we go back up here, right, Q sub x is just this function right here, defined by this equation. And so the subscript of Q is just where along the horizontal axis is the center of this bump, right? So each of the BIs is an example of a QX, but I and X are not equal. All right, so going back now to the lecture notes. Right, so I was saying Rn is a vector space, but it is not even close to the only vector space. There are hundreds or thousands of useful vector spaces out there, and we've seen a bunch of examples. So the homework is one useful but perhaps somewhat complicated example. Right, it's a vector space where the elements are functions. And the elements are therefore specifically not lists of vectors of real numbers, right? They're not elements of Rn. They're functions, which is a completely different object, but a set of functions can still act as a vector space. And the way that that happens is that for something to be a vector, that just means that you can add two vectors together, and we can add two functions together. We just do it element-wise. And we can scalar multiply a vector, which is to say we can multiply a function by 3, which we do by multiplying every function value by 3, right? So it's really important to keep clear the distinction between Rn and a general vector space, right? A general vector space is just something that supports the operations that vectors need to support, which is to say addition and scalar multiplication. And Rn is a specific vector space, which is the one where the vectors are tuples of real numbers. All right. The same thing for inner product spaces, right? So Rn has an inner product on it. That inner product, the one on Rn, is called the dot product. So specifically, the dot product is the one that that we're familiar with, where the dot product between two vectors is the sum of the products of their corresponding elements. There are many different inner products, right? For every set that you can think of to make into a vector space, like functions or matrices or trees or strings or whatever, you can define multiple different inner products usually on each one of these sets. And so every time you define a different inner product, you get a different inner product space. And again, to be an inner product, all that's required to be an inner product space, all that's required is that you have an inner product. So you have to have some way of writing down the inner product between two vectors x and y. That inner product has to satisfy the axioms that we need from an inner product, which is to say that it is bilinear. That just means that it's linear in each argument where you hold the other argument fixed. It's symmetric, and the only way to get x dot x equal to 0 is to have x be the 0 vector. Remember that the 0 vector is the same as the additive identity. It's the vector that when you add it to any other vector, it doesn't change them. Again, we talked about the concept of completeness. That just means that we have a notion of convergence defined on our vector space, and every Cauchy sequence of vectors converges. And that is to say that, so a Cauchy sequence is a sequence that satisfies this property. Pairs of successive vectors get closer to each other, meaning that the norm of the difference approaches 0 as we go farther and farther along in the list. And every Cauchy sequence should converge. That's what it means for a space to be complete. And that's true of Rn, and it's going to be true of every other inner product space that we look at in this class. Right? But when I say a complete inner product space, that just means that there is a notion of limits, and it works. Every Cauchy sequence has a limit. All right? So we talked about a lot of examples of vector spaces. I linked from the syllabus for today. Someone is asking, what is an inner product space? An inner product space is just a vector space where we have defined an inner product, right? So an inner product space, so we start with a vector space, and as soon as we define an inner product that satisfies all of the properties that we need for it, then that vector space becomes an inner product space. All right. So I gave I posted a set of lecture notes. They're linked from the syllabus for today, where we have a bunch of examples of vector spaces. So maybe at this point it would be good for me to switch to these examples, and people can ask questions about the examples. Let me just take a look farther down. So we have vector space of functions is going to be one of the examples, right? And there's an analogy between a vector space of functions and Rn in the sense that if you think of plotting a function, that means to sample the function at a grid of points and pick the values of the function at that grid. So that vector in Rn, where we just collect together the sampled values of the function, that vector behaves a lot like the function itself when we treat it as a vector. And so this example is supposed to show that correspondence. And so one of the main uses of vector spaces for machine learning is to define classifiers. And we went through discriminant functions a while ago. People should feel free to ask questions about discriminant functions. And I will come back to them after we go through the vector space examples. Well, here are the vector space examples. So hopefully hopefully people have had a chance to look at this. These notes have been posted for several days now. But the way we're going to do these examples, well, let's just go through them. So we already went through this example, right? This is the example you're working with in the homework, where the generating set is the set of all functions of the form qx, like this. The generating set just means that the vector space is going to be the span of all of the functions in our generating set, meaning the set of all linear combinations like this. Or if there are infinitely many, as there are in this case, we might have to we might have to allow our linear combinations to be to have infinitely many terms in them as long as the sum converges. Right? So elements of this vector space look like this. This is an example. Right? And we can define an inner product on this. So up to here we have a vector space, but we can make it an inner product space by defining an inner product. And I want to emphasize that there are many possible ways to do this. Even for just this one vector space, there's lots of different inner products we could give, and they all make different inner product spaces. But here in this example, we're defining the inner product between a pair of basis elements to be that the inner product of qx and qy is what you get when you evaluate the function qx at the point y, which, because the function is symmetric around x, is the same as saying evaluating qy at x. Right? So if people are confused about this process, right, confused about this example, please ask questions about it. There are a few things that are potentially confusing, right? First is the idea that the vectors are not tuples of real numbers, but actual functions. Second is the idea that we define the vector space just by listing this generating set and then taking all convergent linear combinations of elements of the generating set. Third is this particular inner product. There's no reason that you should know a priori that this is a valid inner product, but you know, your professor is saying that it is, and hopefully he's a trustworthy guy. You know, I think we gave another example of a different inner product, right, on this same vector space. So if we go back to a blank spot on our slides, right, a different inner product. You could have that the dot product between qx and qy was equal to the integral from minus infinity to infinity of qx of z, qy of z, dz, right? So this is a different inner product, right? But it is very definitely not the one that you're using in the exercise. And so if we pick this inner product instead, we get a different inner product space. Okay, we're getting a question about why do we care about an inner product in the first place? And that's an excellent question. So the reason we care about an inner product is that it allows us to start to do geometry on the space. So before, the vectors are just these, you know, opaque elements. So without an inner product, we can't say anything more than, let's say that the sum of, you know, two vectors is equal to a third vector. Once we have the inner product, we can start to define geometric concepts like orthogonality or being perpendicular. So, for example, two vectors are considered to be orthogonal if their inner product is 0. And so we can start to ask about things like, you know, what is a right triangle in our vector space? Or we could ask about, well, because we have an inner product, that lets us define a norm, right? The norm is defined as the square root. The norm of x is the square root of x inner product x. And so we can start talking about what vectors are close to what other vectors. Without an inner product, there would be no notion of closeness in the vector space. And so a third reason is that it lets us do some interesting stuff. Like, for example, define machine learning algorithms that use this vector space as a data structure. Someone is asking, what exactly is a vector space of functions? So that's a good question as well. Let's get a new blank slide. So a vector space of functions is a vector space, right? So it has to be both a vector space and a vector space of functions. So for it to be a vector space, it's just some set V of vectors, which has the operations of addition and scalar multiplication defined on it. And then in order to be a vector space of functions, that just means that the elements of V, right? So if f is an element of V, that means that f is itself a function. Right? So just being a vector space means that the elements are vectors. We can do things like add them together or multiply them by a scalar. But if we also assume that the elements, in addition to being vectors, are being interpreted as functions, that means that we can do things like evaluate them at a particular point. So that means that our vector space V is going to be a subset of some function set. Let's say, for example, the set of functions of one real argument that return a real value. Right? So going back to this example here, right? This plot here, this is a plot of a function, and this function is an element of our vector space, right? It's just one vector, and then there are many other vectors, infinitely many other vectors that are all different functions, right? They might go like, you know, that, right, or like that. Right? They're all different smooth functions that you can get by adding together basis vectors. Okay. So let's go to another example, right? So here, this is a vector space of strings, meaning that it is a vector space and its elements are strings, right? So what does that mean? That means that our generating set is going to be a set of strings. In particular, we're going to have an alphabet, let's say the set of ASCII characters, and we're going to have strings over that alphabet. Let's say hello or world. Our vector space, so our generating set first is going to be the set of all finite length strings over that alphabet, so all finite length ASCII strings. And then our vector space is going to be the set of convergent linear combinations of those generating elements. So it could be something like 3 times hello plus 5 times world minus 2 times exclamation point. Right? And so here's a generating element, here's a generating element, here's another generating element. We're taking a linear combination of them, and it's a convergent linear combination because it has finitely many non-zero elements. And so this is an element of our vector space. So this sounds like it's kind of a weird vector space, and in many respects it is, but it turns out to be a useful one because we can use it, for example, to talk about machine learning on text documents. So each text document is going to be a string of characters. It's going to be itself an element of the vector space. In fact, it's even going to be a generating element. Oh, somebody's asking me to go back to the functions example. Okay. So the functions example is just that is just here, and they're asking what does it mean to be an inner product of functions, right? So I guess there's 2 answers to that, right? There's the mechanistic answer, which is that it just means this definition right here, this mathematical expression. That's not necessarily very helpful. So let's say, what does it mean in a higher level sense? So an inner product of functions is just an inner product which works on an inner product space, right? Because that's where an inner product is defined. And that inner product space, its elements are functions. And so the arguments to the inner product are 2 functions, 2 elements of our inner product space. So here qx is a function, qy is a function, and we're defining the inner product of those 2 functions by this expression. Right? So in general, when I say, you know, an X of functions, a vector space of functions, an inner product of functions, anything like that, that just means that we're working with a vector space or an inner product space whose elements are functions. And I could say the same thing, a vector space of strings, an inner product of strings. We would be working with a vector space or an inner product space whose elements are strings. All right. And what does it mean to be an inner product? Again, an inner product is a function that's got two arguments. Each of those two arguments is a vector. So in this case of our vector space of functions, each of those two arguments is a function. And the inner product has to return a single real number. So it gets two, right? So going back here, we have that the inner product, which I'm just going to write that way, right? It's a function which goes from pairs of vectors, v cross v, and returns a single real number, right? And it has to satisfy some properties. So the key properties are one, that it has to be bilinear, meaning that if you hold one argument fixed, it's linear in the other arguments. So like, for example, f plus g inner product with h, right? That's equal to f inner product with h plus g inner product with h, right? And same thing, 3f inner product with h is equal to 3 f inner product with h, right? And the other one is that the inner product of vector with itself is equal to 0 if and only if the vector itself is the 0 vector, right? And so being an inner product just means satisfying these properties, right? It has to take two vectors as arguments, linear in each argument while you hold the other one fixed, and it's only 0 the only way for a dot product of a vector with itself to be 0 is if that vector is itself the 0 vector. All right. So let's go now to the string example, right? So I defined now a vector space of strings. And here, actually, the vector space includes more than just strings. It includes linear combinations of strings. And we don't have a direct interpretation of that. There's no interpretation to this expression, 3 hello plus 5 world minus 2 exclamation point. The only interpretation of that expression is this expression, right? There's no underlying meaning to it. And that's in contrast to functions, where we think of a linear combination of functions as being taken component-wise. You can still evaluate that linear combination of functions. Okay, so now it's a vector space, and I would like to make it as well an inner product space. And so in order to do that, I have to define an inner product. And the way I'm going to do that is I'm going to define an inner product on the generating elements. And there's a lot of ways to do that. But one of them is the one listed in this example. We'll set the inner product between a pair of vectors to be the number of common substrings in those vectors. For example, the number of common substrings between ard and vark is 4, right? They have the empty string in common, they have the string a in common, they have the string r in common, and they have the string ar in common. Right, so again, that's just a definition, and you can go ahead and prove that it has all of the required properties to be an inner product, but that's sort of beyond the scope of this class. We're just going to assume that it has the required properties, and in fact it does. And there's a bunch of ways to do this, right? So it could be, for example, that we put length restrictions on the string. We only count substrings of length at least 1, skip the empty string, or only substrings of length at least 3, so that we don't worry about short substrings. We could count substrings with repetition, so that, for example, this we counted as having the substring a twice, as opposed to just once. As opposed to just having it or not having it, right? 0 or more than 0. Or we could allow substrings that skip over characters, so that lone and loon share the substring lo skip n, right? And so you could think of learning a text classifier with this, where we determine whether an email is spam by looking at how many substrings it has in common with other emails that we've seen that we know are spam. All right? And so hopefully at this point you should be convinced that there are vector spaces with whose elements are lots and lots of different useful, interesting objects, right? They're not, they're in no way restricted to being tuples of real numbers. They can be, well, we've seen functions and strings so far, and we'll see trees and derivative operators farther down in this document. But that's even like a small sampling of the useful spaces that people have defined. All right, so let's move on to trees. And the tree example is going to be a lot like the string example. We're going to, again, have a finite set of labels, and we're going to look at all of the binary trees whose nodes are labeled, right? So if our labels are red, green, and blue, here's a binary tree where the nodes are labeled with red, green, and blue. And vectors, as they always are linear combinations of elements of our generating set. So we could have 3 times this tree plus 5 times that other tree, right? And we could have any linear combination of these trees. And this is a vector space. It becomes a lot more useful if we turn it into an inner product space by defining an inner product. And so let's define an inner product on this particular vector space by counting common subtrees. And again, as before, we'll define the inner product on the generating set and extend it to the rest of the vector space using linearity. And so here, we're going to define the inner product between this tree and this tree by counting how many subtrees they have in common. And so the answer here is 6, because these two trees share the share the empty subtree. They share the subtree of just having a red node, right? So here's a red node in this tree, here's a red node in this tree. They share just a green node, they share just a blue node, and they also share this subtree of a blue node whose right child is green, right? Here it is in the first subtree, here it is in the second subtree. And they have the subtree of a red node whose left subchild is green. Here it is in this subtree, and here it is in this subtree. And again, there are tons of variants of this. For example, we could look only at initial subtrees that start at the root, or final subtrees that go all the way down to the leaves, although they might not go all the way up to the root, right? And we'll get different inner product spaces every time we describe a different inner product. So there's a question about how addition is defined on trees, right? And remember, addition is defined on all vectors, not just trees, right? And so it's defined on a linear combination of elements of G. And so it's defined the way a linear combination would typically be defined, which is to say that, let's again get ourselves a free blank page, right? So if we have 3 times red, green, blue, green, plus 5 times blue, red, green, green, right? So that's one vector, and we want to add it to, let's say, 2 times the subtree red, green, blue, green, minus 7 times the subtree red, green, green, right? So we just add them together, right? So these two elements, the answer is that it is this whole expression, 3 times this plus 5 times that plus 2 times this minus 7 times that. And then we can factor out, because 3 multiplies this subtree and 2 multiplies the same subtree, that's equal to 5 times that subtree, red, green, blue, green, plus, and now this one doesn't combine with anything, so it's 5 times, blue, red, green, green, minus 7 times this subtree, which also doesn't combine with anything. Right? And so we simplify as much as possible because we know that scalar multiplication distributes over vector addition, 3 times that plus 2 times that has to equal 5 times that, the same thing, right? But there's no other simplification we can make here. Somebody is asking, if you have a vector from a vector space of functions, what is the ith element of that vector? The answer is there is no ith element of that vector, right? There is no operation of taking the ith element of a vector. Vectors only have the operations of addition and scalar multiplication, and possibly inner product if we're in an inner product space. There is no way of taking the ith element of a vector in general. There is, of course, a way of taking the ith element of a vector in Rn, right? So Rn is a special vector space in that it has a representation as a tuple of real numbers. And because it has a representation as a tuple, we can do tuple things on it, in particular take the ith element. But other vectors don't have representations as tuples, and so there's no way to take the ith element of that vector. All right, so let's go to the last example in this set of notes, which is differential polynomials. So this vector space is useful. You may have worked with it before if you took a course on differential equations. It's the vector space of operators that act like derivatives. And so in particular, let's define dk as the operator that takes the kth derivative of a function. And let's assume that we're working only with real valued functions of a single argument. And we're going to assume that we have some set of functions that are differentiable, meaning that dk actually makes sense on them, and that it's closed under dk, meaning that if you take the kth derivative, you still get a function in our space. All right? So an example of a space that would work for this is the space that we defined a few sections above, right? The space that you guys are doing an exercise on right now, where the elements are linear combinations of these Gaussian bump functions. Okay, so we have some vector space of differentiable functions, and now we're going to use that to make a different vector space. We write dk for the operator that takes the kth derivative. And dk is itself a linear operator because the derivative of 3 times a function is 3 times the derivative of that function. And now we're going to take our generating set to be dk for k equals 0, 1, 2 up to every natural number. Then our vector space is going to be the space of linear combinations of elements of G. So for example, it could be 3d squared minus 5d plus 5, right? And this is a linear combination of generating set elements. And it's also interpretable as itself a differential operator that we could apply to a function. In particular, it turns the function f into 3 times the second derivative of f minus 2 times the first derivative of f plus 5 times the 0th derivative of f, which is to say just f itself. All right? And I can't off the top of my head think of a useful inner product on this space, but I'm sure people have come up with inner products that they've defined on this space. So right here, this is just an example of a vector space, and we could think about multiple different ways to turn it into an inner product space. Okay. All right, so those are all of the examples. And let's go back now to looking at the notes. And again, as I said, for anybody who's joining us late, what I'm doing right now is going back over the past like 3 or 4 classes worth of lecture notes and taking questions that people have and trying to do, I'd be willing to do worked examples on any topic that anybody is interested in seeing a worked example. All right, so what are vector spaces good for? Or specifically, what are vector spaces of functions good for? One example is that we can use them to define classifiers. So you guys already did an example. where you got a Fisher discriminant for a for some points in the plane, and that discriminant was an element of a vector space, and in order to find that discriminant, we had to do a bunch of operations on that vector space, right? So let's look at what the Fisher discriminant does first on a very simple vector space, R2, right? So the Fisher discriminant is just a linear function on that vector space, w dot x minus b. And if that function is positive, we split into one class, and if it's negative, we split into the other class. And the Fisher discriminant specifically is a way of finding this parameter vector w. W is the difference between the class means, right? And so we're doing a vector space operation here, right? In order to take the mean, we have to add together elements of the vector space and then divide by the number of the elements we added together. So adding them together is vector addition, and dividing by the number of elements is scalar multiplication. And so here we're doing vector space operations on the training data. And again, here to compute this mean of the other class, we're doing vector space operations on the training data. And now, so that's to find W. And to find B, we're actually also doing more vector space operations, right? Here's addition, scalar multiplication. But now we're also doing inner product space stuff. We're taking the inner product of W with this vector that we computed this way, right? And it turns out, we went over this in class, that taking W and B this way makes the class boundary be the perpendicular bisector of the line connecting the mean of the X class to the mean of the O class. All right. So that's Fisher discriminants in R2. And in R2, we were finding our parameter was a vector in R2, right? It was W. And so if we're working now in a function space, our parameter that we're trying to find is going to be a vector in this vector space, which is to say itself an entire function. And that function is going to be interpreted as our discriminant function. So we're trying to find the discriminant function directly. Before we get there, we're going to do a slightly more complicated example in a finite dimensional vector space. So here's an example where a linear discriminant isn't going to work very well. Right? It's an example where you really want like a circular discriminant, which is to say you want your discriminant, you want your class boundary to be a conic section, which means you want your discriminant function to be quadratic. So to make our discriminant function quadratic, we had this trick where we had a feature map, which we called phi, and we took a point in R2, which I'm calling x, and we turned it into a point in R5 by a given operation. And now we're looking for a vector in R5 such that we can, when we take w dot phi of x minus b, that's going to be our discriminant function, right? And so we're representing now a very simple function space, right? The set of quadratic functions. And we're representing it using a vector of real-valued parameters. But we can think of it either as a vector of five numbers, the real-valued parameters. 6 numbers, I guess, if you count b. We can think of it either as a vector of a finite set of numbers, or we can think of it as itself a quadratic function. And those are two different vector spaces. But there's an obvious mapping back and forth between them, right? You have the parameter vector for a function, and you have the function itself. And it turns out that the same recipe works just fine. All that we need to do is replace x by phi of x, right? Do the feature transform before we take the class means and before we do the all of the vector space operations to get the discriminant. And if we learn the parameters w and b this way from that above set of data, then if you excuse me, look at the discriminant that we get that way, I'm plotting here the 0 level set of the discriminant, which is to say the boundary between classes, and it looks like it works pretty well in this case. It successfully separates the circles from the x's. All right. And so the next set of lecture notes functions, lecture notes is about learning the discriminant function directly. the discriminant function no longer has an interpretation as a simple list of real parameters. It is itself just a function, which is an element of a vector space of functions. And so let's move on to that next set of lecture notes. All right, so we talked about linear combinations, right? So linear combination is just some function of this form where the ai are scalars and the xi are vectors. And you can add together two linear combinations in the same way I just illustrated here, right? You just concatenate the two sums and you collect any terms that you can. So in this example, I could only collect this pair of terms to make that term. A linear combination of vectors sums up to another vector. If that vector happens to be the zero vector, that's interesting. And that's what's going to let us define linear dependence or linear independence. So a set of vectors will be linearly dependent if we can sum them up with non-zero coefficients but still get the zero vector as the result, right? So here's an example in R2. If we take this vector plus this vector minus this vector, we'll get the zero vector, which is 0, 0. And so these vectors are linearly dependent. If vectors are not linearly dependent, in other words, if the only way to get 0 as an output is to set all of the coefficients to be 0, then the vectors are called linearly independent. And so, for example, this pair, the first two vectors here are linearly independent. So are the last two, right? So is the first and the last. Okay. And so linear dependence or independence is going to be a really important property of a set of vectors. It's going to wind up letting us define, for example, the dimension of a vector space. And so let's see. Okay, so if we have a linearly independent set of vectors, and if that linearly independent set is maximal in the sense that we can't add another vector without making it dependent, then we have a set that's called, that we'll give a special name to. We'll call it a basis. And the size of the basis is called the dimension of our vector space. And this is the idea of dimension that we're all used to, right? A plane is a two-dimensional vector space. We live in a three-dimensional world, right? So R3 is a three-dimensional vector space. A line is a one-dimensional vector space. A point is a zero-dimensional vector space. And the geometric interpretation of linear independence is that no k of your vectors lie in a k-1 dimensional subspace. So no two, in a plane, no two vectors can lie on the same line. Or in 3 space, no 3 vectors could lie on the same plane, right? And that's the geometric interpretation of linear independence. And if we can make a basis, if we can make a linearly independent set of an arbitrarily large size, we're going to say that our vector space is infinite dimensional. And so I already gave this example. Our vector space of functions is infinite dimensional. We've gone over inner products already. If people have more questions, feel free to ask. But here's our linear classifier in infinite dimensions. We're going to have a classifier of this form. We'll have W, which is itself a vector in our vector space of functions. So W is a whole function. We have our inner product between W and phi of x. So phi of x is a way of taking a point in our example space, so a point in the plane, and turning it into a function. And the inner product between this function and that function minus the scalar b, that's a function, and we can use it as our discriminant function. And so we can get something that looks like this as our class boundary. And we get it using the exact same formula that we did before, right? For each one of our training points, we use the function phi to make it into an entire function in our function space. And we take the mean of those functions in the x class and the mean of those functions in the o class, and w is the difference between those two means, right, and so forth. So I think I have on the next set of lecture notes, yeah, here's the contour plot of the entire discriminant function that we learned that way, right? So here's the entire discriminant function, and if we go back, right, here is the class boundary, which is one of the contours in the contour plot. It's the zero level set of the function. But this is a better representation of the entire function, right? And I've shown our training data as well on the same plot, right? So that you can see that the zero level set does in fact separate the x's from the o's. Okay. So let's see. We've done a little bit of geometry already, but let's keep on doing geometry. If we have a linear function, then w dot x, w is going to be the normal to the plane defined by that linear function, right? We define a plane as the zero level set of the linear function, and w, the parameter of the linear function, is the normal to the plane. And if we plot the whole function, right, so here's a contour plot of the whole function, w is the gradient, meaning the direction of steepest increase of that function. And then we can shift the plane back and forth by taking the intercept to be non-zero, right? So I did some examples of that in class before, but I'll draw another one, right? So if we have here's our axes, here's our vector. If we take the intercept to be 0, it's going to define this plane. If we take the intercept to be positive, right, so this is b equals 0. On this side, it's going to be b greater than 0, right? So that means moving the plane forward along the vector. And if we go this way, it's going to be b less than 0, right? So an example of a plane down here, this might be b equals -2, in which case this would be b equals +2. Okay. So let's move on now to the next set of lecture notes. Right, and so this was the set of lecture notes that I covered on Monday, but I think I'm going to need to go through them again because if people didn't understand what vectors were before going to these, they would have trouble understanding these lecture notes. So let's go through them again. So here's the definition of a linear function, right? It's a function such that f of ax plus b is a f of x plus b, f of ax plus by is a f of x plus b f of y. And linear functions are pretty important. And we're going to work with linear functions that go from one vector space u to another vector space v, right? And so for these, again, you should think if your vector spaces are Rn or Rm, you should think of a matrix. So that f of x is just multiplying by a matrix A. But there are a lot of other examples, such as the differential polynomials that we looked at before. Right? And so again, for coordinates, we talked about the difference between a general vector space and Rn, right? And coordinates are a way to provide a mapping between a general vector space and the vector space Rn, right? And there's a good reason for that. Our computers are really good at storing tuples of real numbers, and they're really bad at storing anything else. And so in order to work with vectors in a general vector space, we need to represent them as tuples of real numbers. And so the problem that you're trying to solve for the exercise that's due today is exactly to come up with this coordinate representation, right? And so to do that, right, what we need is a basis for our vector space. And there's a way, part of what it means to be a basis is that any vector in our vector space X, we can express it uniquely as a linear combination of basis vectors. And so those weights in that linear combination, we can take those as coordinates for our vector, right? And so we have X, which is in our original vector space. It might be a function, a tree, a linear combination of trees. And we have this other vector in Rn, and we're making a mapping back and forth between two of them. And that mapping is the mapping of giving our abstract vector coordinates. And there's no canonical way to do this, right? Anytime you have a different basis, you get a different set of coordinates, and there's no one basis that's better than any other basis. You just pick a basis and you work in that one. And then you get your coordinates. And the exercise, right, it talks about not just that there is a way, but there's a computational way to do it, right? There's an algorithm which is described at the top of the exercise for coming up with these numbers x tilde. All right, so we have linear operators that go between vector spaces, and we have coordinate representations for vectors. So we'd also like to make a coordinate representation for linear operators. And that coordinate representation is going to be a matrix, right? And it's going to be a matrix that we choose in such a way that, well, going down to the bottom here, right? If we have a vector x in our vector space U, and the linear function L applied to x is equal to y, which is a vector in V, then the same thing is going to happen when we use the coordinate representations. If x tilde is our coordinate representation of x, L tilde is our coordinate representation of L, then if we multiply this vector by that matrix, we get the coordinate representation of the vector y, right? And so I have an algorithm written out up here for coming up with that matrix that's the coordinate representation of the linear operator L. The details of that argument, I can go over them if people are confused about it, but at the top level, all you need to know is that there is an algorithm that will, given a linear operator and bases for the domain and range spaces of that operator, it will give you the matrix that corresponds to, that is the coordinate representation of the linear operator. Somebody's asking if the goal of the exercise for today is to find the coefficients for a vector, right? So here, yes, we have a vector. In the exercise, it was called f because it was a function, and it's a coordinate. It has a coordinate representation in terms of these x tilde, the scalar, and the basis vectors. We've given you f, and we've given you the basis vectors v, and so to come up with a coordinate representation, all you need to do is to find those scalars x tilde sub I. Right? So that is, in fact, what we were asking you for in the exercise. And then given those scalars, we're asking you to work with the function that is represented by those scalars. In particular, we're asking you to make a plot of that function. All right, so we have now a matrix that corresponds to a linear operator. We can do useful things with matrices. So in particular, we can take slices out of them. Some of the important slices are to take columns out of a matrix. So L of colon comma 2 is the column 2, 5, 8, right? Or L of 3 comma colon is the row 7, 8, 9. We defined matrix transpose. We also defined the adjoint of a linear operator. And the way that you work with an adjoint is that it corresponds exactly to matrix transpose. So if you have a matrix that represents your operator, then the transpose of that matrix represents the adjoint of your operator. Similarly, there's an inverse operator, right? And there's inverse in the sense of functions, right? If you apply a function L to x to get y, then you apply L inverse to y to get x. And there's inverse in the sense of matrices, right? You get the inverse matrix, and those correspond. The inverse matrix, multiplying by that, implements the inverse function of multiplying by the original matrix. And we also have pseudo-inverses for the case when inverse is not possible to define. Let's see, we talked about matrix patterns like diagonal, triangular, orthogonal. I'll skip over those unless people have questions. And we talked about the property of being positive semi-definite. And that's an important property as well. We'll run into it again later. In particular, we'll often run into symmetric PSD matrices or symmetric self-adjoint PSD operators. And those two things correspond to each other. All right. So now that we have linear operators, we can define linear equations. And so for this set of lecture notes, we're going to be working completely in coordinate representations, because one of the most important things to be able to do for working with linear operators is to be able to solve linear equations that are represented in a computer, right? And you'll need to do that for today's exercise, right? You'll need to write out a matrix and a vector that define a linear equation and solve that, that linear equation. And there's a lot of ways to solve linear equations, but probably the single most common is LU decomposition followed by back substitution. So LU decomposition, we start by factoring our matrix A. So we're trying to solve the linear equation AX equals B. So A is an n by n matrix, B is a length n vector that's given, and X is the vector we're trying to find, also length n. We factor A into the product of a lower triangular and an upper triangular matrix. And then we solve the equations with the upper triangular matrix, and then another set of equations with the lower triangular matrix, and we get a solution to the original set of equations. SVD. People are wondering how to plot a function that's represented as a sum of basis functions. So let's get ourselves a new, right? So we have f is equal to the sum from I equals 1 to n of xi tilde bi, right? And we want, we know how to add functions, right? So f plus g of x is equal to f of x plus g of x. And we know how to scalar multiply functions. So a times f of x is equal to a times f of x, right? So we can apply that here. F of x is equal to sum I equals 1 to n x tilde I bi applied to x, right? And that's equal to, we'll just pull it out, sum from I equals 1 to n of xi tilde bi of x, right? And so that's how you evaluate a function that's represented as a linear combination. I think I posted about that on Piazza, but it's good to go over it in front of the whole class as well. All right, so let's go back now to solving sets of linear equations. Right, so I wanted to point out you should never solve equations, or almost never, by directly computing the inverse, because A, it can be very expensive, and B, it can give you the wrong answer, because of round-off errors. So we should instead solve equations using a factorization, like LU decomposition or like the singular value decomposition. If we have a matrix that's singular, meaning not invertible, we can still find an approximate solution to AX equals B using the pseudo-inverse. The pseudo-inverse is defined so that X equals A pseudo-inverse B will give us something that minimizes the norm of the residual vector AX minus B, right? And so we need a way to compute that pseudo-inverse, and the SVD is a good way to do it. We just take the singular value decomposition, A equals USV transpose. If we inverted this directly, it would give us V S inverse U transpose. But then we can't invert that for a singular matrix, and what's going to happen is that some of the diagonal elements of S will be 0 in a singular matrix. And so what we do is we just replace 1 over 0 by 0 in that pseudo-inverse, and we're done. So the pseudo-inverse of A is going to be U times the is going to be V times the pseudo-inverse of S times U transpose, this expression right here. And the way you calculate the pseudo-inverse of a diagonal matrix is every non-zero diagonal element, you just take 1 over that element. Every zero diagonal element, you just leave as 0. And if we're close to singular, we can actually just take really small diagonal elements and replace them by 0. All right. So we talked about subspace span and orthogonal complement, right? So two vector spaces U and V are U is a subspace of V if U is just a subset of V in the sense of just set containment, and U and V are both vector spaces, right? So subspace is just what we call a subset when both of the things in question are vector spaces. If we have a strict subspace of our vector space, then we can take the orthogonal complement of that subspace, and geometrically that's just the set of vectors that are orthogonal to every vector in our subspace. So let me write that, right? So another way of defining the orthogonal complement of S, that's equal to y in our original vector space such that x inner product with y is equal to 0 for all x in S, right? So that's one way to define the orthogonal complement. Geometrically, it just looks like, you know, we have our ambient vector space V. We have some subspace, let's say like that, the xy plane, and we take everything that is orthogonal to that, right? So this is S, and this is S orthogonal complement. Right, and I'll just, for clarity, write a little orthogonality sign there. When you're working with linear equations or with matrices, there are basically two really important subspaces for any matrix, which is to say its span and the null space of the transpose. And those spaces are important because they make a decomposition of the whole vector space into a sum of two orthogonal subspaces. So the range and the null space of the transpose are orthogonal to one another, and their sum is the entire vector space. This is sometimes called the fundamental theorem of linear algebra. And there's something equivalent for a linear operator. All right, so, and then we've already gone through this, and I think there's no point in starting a new topic on matrix differentials. with 5 minutes left in the class. So, you know, people ask questions quickly if you want me to spend another 5 minutes answering them. Otherwise, we will go ahead and end class. And I have office hours right after class. I'm able to stay until 3:30 in office hours. So if you have questions for me, please try and ask them to me before then. All right, thanks a lot, everybody. And we'll see you next time.